Imagine the absolute worst-case scenario for a bridge. A 100-year earthquake hits in the middle of a Category 5 hurricane, exactly as a heavy military tank convoy is parked dead center on the main span. If an engineer were forced to design a structure to effortlessly resist 100% of all those kinetic forces at the exact same time, the result wouldn't look like a bridge. It would be a solid, prohibitively expensive block of concrete. Absolute invulnerability is an irrational engineering goal. Building an invincible structure demands a volume of materials and capital that simply does not align with physical or economic reality. To bridge the gap between absolute safety and actual construction budgets, engineers rely on probability. Instead of just piling on mass to counterweight, they use a codified algorithm to define a realistic envelope of survival. In India, that probabilistic algorithm is maintained by the Indian Roads Congress. Specifically, a document known as IRC 6, which parameterizes every environmental and operational force a highway bridge will ever face. This matrix is Table 1 of the IRC 6 code, and it dictates the structural destiny of those bridges by establishing exactly how different stresses must be calculated. The architecture of this matrix is highly specific. Look at the far left column. These rows represent discrete, isolated physical threats: live load, wind, seismic forces. Now look at the top row. Columns 1 through 9 dictate exactly how these individual threats are forced to interact. To understand how a bridge actually survives, we have to deconstruct this matrix. We need to work backward from the physical forces that populate its rows before seeing how they combine. Table 1 functions as a comprehensive map of every kinetic threat a structure will face over its service life. We start with the live load. In bridge engineering, traffic is categorized into specific classes based on extreme industrial or military use, like these Arjun main battle tanks. This diagram models the Class A tracked vehicle load. It dictates a specific geometric footprint, defining how weight is distributed along a 3.6-meter track. It also enforces strict spacing rules, like a 90-meter clearance between vehicles, which dictates the maximum bending moment. By contrast, this illustration models the Class A train of vehicles, representing standard heavy commercial transport on permanent bridges. It assigns precise individual axle loads, 11.4 tons, 6.8 tons, and 2.7 tons, separated by exact distances. The designer's task is kinetic. Engineers must mathematically drive these rigid two-dimensional axle footprints across the influence lines of their design to locate the absolute maximum point of structural stress. A bridge structure isn't broken by total mass alone. It breaks based on the localized density and geometric arrangement of the axles applying that mass. Static weight is a mathematical fiction. Vehicles bounce, break, and slam into joints, generating dynamic shockwaves through the deck. IRC-6 normalizes this dynamic violence using an impact factor, a calculated percentage increase added directly to the live load to account for kinetic shock. This graph plots the impact percentage curves for different structures. It reveals that the kinetic penalty is not universal. It is heavily dependent on the physical span length of the bridge. A short span absorbs massive dynamic shock, triggering an impact penalty of 25% or more. But as the span gets longer, the massive superstructure dissipates that exact same energy, resulting in a drastically lower penalty, often below 10%. The span's physical length dictates the structure's intrinsic vulnerability to kinetic violence. Next, we pivot from top-down gravity loads to lateral environmental forces. These are the kinetic threats that attempt to push the bridge sideways, specifically river currents striking the substructure. The code defines river current intensity using a strict formula, P equals 52 kV squared. Engineers have zero control over V, the velocity of the river, but they completely control K, a constant representing the physical geometry of the pier itself. This drawing outlines codified pier shapes. A square-ended pier creates massive turbulence against its flat face, earning a punitive K value of 1.50. But by introducing cut and ease waters with equilateral arcs, the geometry smooths the current, drastically dropping the K value to 0.45. Look at the fluid dynamics. By merely changing the shape of the concrete from a flat square to a point, the engineer mathematically erases over 60% of the hydrostatic pressure acting against the bridge. The shape of the bridge substructure acts as an active defense mechanism. It fights the river's kinetic energy before the internal materials ever have to bear the load. This matrix brings all those isolated parameters together. Now that we understand the individual forces, live load, impact, water current, we can see how the code dictates their combination. Column I represents the daily reality of the bridge. It forces the engineer to combine dead load, live load, impact, and water currents, assuming they are all operating at 100% intensity simultaneously. Then we move to the extreme survival scenarios. Columns 7 and 8 inject massive, rare events into the equation, activating the rows for peak seismic forces or cyclonic winds. The code provides a built-in safety valve for these extremes. Rather than bulking up the bridge with more steel and concrete to handle the earthquake, the matrix allows the permissible stresses of the materials to be pushed to 150% of their normal limits during those specific combinations. The IRC does not demand the bridge remain perfectly rigid against an extreme disaster. It allows the materials to be pushed to the absolute ragged edge of their capacity during rare events, specifically to save on structural mass and construction cost. Why is it statistically acceptable to let a bridge experience 150% of its normal operating stress during a seismic event? This is the core concept of probabilistic design. The odds of the heaviest military convoy hitting the exact worst geometric point on the span at the precise millisecond of a 100-year earthquake are infinitesimally close to zero. Designing a structure to stay comfortably within normal stress limits during that statistically impossible overlap would be an immense waste of natural resources and capital. The IRC code discounts overlapping extremes precisely because it acknowledges statistical reality over blind paranoia. IRC.6 is not a static safety manual. It translates the chaotic variables of traffic geometry, fluid dynamics, and natural disasters into a rigid, mathematically executable framework for survival.